sklearntreeExtraTreeClassifier. Description: ExtraTrees classifier is an ensemble learning method for classification that operates by constructing a multitude of decision trees during training and outputting the class that is the mode of the class is classification or mean average prediction regression of the individual trees. The trees are built in a completely randomized way, meaning that at each node, a random subset of features is chosen from the total set of features, and the best split among the chosen features is selected. This randomization process leads to a high degree of diversity among the trees, reducing the risk of overfitting and improving the model's generalization ability. Inputs: X. This input represents the training data, typically a 2D array of shape n samples. N features. Each row represents a data point, and each column represents a feature. Y. This input corresponds to the target variable, a 1D array of shape n samples, containing the class labels for each data point in X. Outputs: fitted model. After training, the ExtraTrees classifier model learns a set of decision trees that can be used to predict class labels for new, unseen data. Predicted class labels for a given input dataset X. The model outputs predicted class labels for each data point. Steps: tree construction. The algorithm creates a specified number of decision trees. Each tree is built on a random subset of the training data and a random subset of features. Splitting criteria. At each node, a random subset of features is selected. Then, the best split among the chosen features is determined based on a criterion like Gini impurity or entropy, aiming to maximize information gain. The split is chosen randomly among the best splits, introducing further randomness. Prediction: to make a prediction for a new data point, the model passes it through all the decision trees. The output of each tree is the predicted class label. The final prediction is determined by the majority vote most common class label among the trees. Metrics: accuracy. This metric measures the proportion of correctly classified instances. It's calculated as the number of correct predictions divided by the total number of instances. Precision. This metric quantifies the model's ability to correctly identify positive instances true positives among all instances predicted as positive true positives false positives. Recall, also known as sensitivity. This metric evaluates the model's ability to correctly identify all positive instances true positives among all actual positive instances true positives false negatives. F1 score. This metric combines precision and recall into a single value, providing a balanced measure of the model's performance. It's the harmonic mean of precision and recall. Visualization plots. Decision tree plot visualizes the structure of the decision trees, showing the decision nodes, branches, and leaf nodes. Feature importance plot displays the relative importance of each feature in the decision-making process. Features with higher importance contribute more significantly to the model's predictions. Fine-tune parameters. Estimators. The number of trees in the forest increasing this value generally improves performance but can also increase training time. Criterion. The function to measure the quality of a split. Common options include Gini impurity and entropy information gain. Max depth. The maximum depth of each tree. Limiting the depth can prevent overfitting by reducing the complexity of the trees. Min samples split. The minimum number of samples required to split an internal node. This parameter helps control the size and complexity of the trees. Min samples leaf. The minimum number of samples required to be at a leaf node. Similar to min samples split, it regulates the size of the trees. Max features. The number of features to consider when looking for the best split at each node. It can be an integer absolute number, a float proportion of features, or auto all features. Bootstrap, whether bootstrap samples are used when building trees. If true, each tree is built on a random subset of the training data. Promoting diversity. Uncertainty methods. Confidence scores. The model can provide confidence scores for each prediction, indicating the certainty of the classification. Higher confidence scores suggest stronger predictions. Out-of-bag OOB estimates. If Bootstrap is true, the model can generate OOB scores. These scores represent the average prediction error for each data point using trees that were not trained on that data point, providing a measure of prediction uncertainty. Challenges and fixes. Challenge 1. High variance due to the inherent randomness in the tree construction process. XtraTreeClassifier can exhibit high variance. This means the model's performance can fluctuate significantly when trained on different subsets of the data. Sample use case. When training an XtraTreeClassifier on a dataset with a limited number of samples, the model's performance may vary greatly depending on the specific data points included in the training set. Fixes to challenge 1. Increase the number of trees. Estimators. A larger number of trees helps average out the variance across the ensemble, leading to more stable predictions. Adjust the max depth parameter. Limiting the maximum depth of the trees can help reduce the complexity and variance of the model. Utilize bootstrap sampling. Using bootstrap sampling introduces additional randomness in the training data, further reducing the risk of overfitting and high variance. Challenge 2. Feature importance interpretation. Interpreting feature importance scores from XtraTreeClassifier can be challenging, especially when dealing with correlated features. Sample use case. If two features are highly correlated, XtraTreeClassifier may attribute the importance of the prediction to one feature while the other remains seemingly unimportant, even if both are contributing equally. Fixes to challenge 2. Feature selection. Applying feature selection techniques beforehand can help identify and remove redundant or irrelevant features, making the interpretation of feature importance scores more reliable. Domain expertise. Utilizing domain knowledge can provide insights into the relationships between features and help interpret feature importance in the context of the specific problem. Permutation importance. Calculating permutation importance, which involves shuffling a single feature and observing the impact on model performance, can offer a more robust measure of feature importance.